we're picking up our discussion on enthalpy, and we're going to pick up in our outline at letter D. And letter D is going to be different ways we can calculate delta H. And there's going to be three different ways we're going to look at. Our first way is referred to as Hess's Law. And Hess's Law essentially states that chemical equations can be written as the sum of two or more these steps. And we might say that delta H of reaction is equal to the sum of delta H of reactions for each step. And we typically use this for heats that are hard to measure, just for reactions that are hard to measure directly. Alright? So again, why do we use Hess's Law? For equations or for reactions that are hard to measure directly. If we're certain of energies that are given off for other reactions, we can add these up and get a pretty good estimate of what the delta H of reaction should be. So our example is going to be, if we had this equation, two carbons that are solids plus hydrogens as a gas yield C2H2, and this is going to be as a gas. What is the energy, or the delta H, of this reaction? Okay? And something like this in your book would be set up so that we could, it would give us a series of steps, and these are the specific steps that the book might give us. C2H2 as a gas plus 5 halves oxygen as a gas yields 2 carbon monoxides, which are gases. I'm sorry, 2 carbon dioxides, which are gases, and water as a liquid. And this reaction, which has been measured lots of times, we know is exothermic, and it's negative 1299.6 kilojoules per mole. There should be a decimal there. It's not letting me put the decimal there. There we go. And that's kilojoules. Another equation we might have that would probably be given to us, we would not typically have to look this up in the back of a book, but carbon plus oxygen yields carbon dioxide gas, and this equation is exothermic as well, and it's negative 393.5 kilojoules. And the third equation is going to be hydrogen gas plus half an oxygen gas yields liquid water. And this is yet again exothermic, and it is exothermic such that it gives off 285.9 kilojoules of energy. Alright, so with Hess's law, you're given equations, and really want to know how did these three equations sum up to this equation. Okay? And in order to do that, we're going to kind of look at where are our reactants and products. So in this first equation, I'm just going to label it maybe equation number 1. Then we have equation 2 and equation 3. In equation 1, notice we have C2H2, which is a reactant, but in our real equation we have C2H2 as a product. So for equation 1, I am going to reverse it. So I'm just going to put reverse 1. And if I reverse that, I'm going to just put my products as my reactants as my products. So we're really going to switch this so we have two carbon dioxides, which are gases, react with water, which is a liquid, and this produces C2H2 gas and 5/2 oxygen gas. And because I reversed that, my delta H is going to be the opposite. Okay, so instead of negative 1299.6, it is going to become positive 1299.6. Because if I have the same products and reactants, but they are switched, instead of giving off 1299 kilojoules, it's going to absorb 1299.6 kilojoules. If I look at my next thing, notice I have carbon, so my reaction 2, I have carbon, and I have carbon as a reactant on both of these, but notice the second one I have two carbons, and in this first, in my step, I only have one carbon. So really I want to multiply step 2 by 2. So I'm going to go to 2 carbons, which are solid, and I'm going to react those with 2 oxygens now. And that is going to give me 2 carbon dioxides. And because we double our moles, we are also going to double our delta H. Okay, because we've doubled everything, whichever the heat that's given off, it should double as well. So this becomes negative 787 kilojoules. If I look at my last reaction, again I have hydrogens as a reactant, I have hydrogens as a reactant. I don't think I have to do much to change this. I'm just going to write this down here. So I've got hydrogen is a gas, and it reacts with half an oxygen as a gas to produce some liquid water. And because I didn't do anything with this equation, my delta H is going to remain the same. So negative 285 kilojoules. Alright, so now if I look back over here in my 3 equations, if I start adding stuff up, there's probably several things I can get rid of. So I'll kind of look at stuff. I happen to have 2 carbon dioxides on the reactant side and 2 on the product side, so I can get rid of those. If I look at this, I've got a mole of liquid water as a reactant, I have a mole of liquid water as a product, and then I also have 2 moles of oxygen and a half a mole of oxygen, so that's 2.5 moles of oxygen, and 5 divided by 2 is 2.5, so my oxygens also go bye-bye. So if I look at what I have left, I really have 2 carbons as a solid, plus hydrogen gas, and all of that yields C2H2 gas. So notice this equation is identical to the equation I began with. So now all I have to do is just add up my new delta H's, and I get something that is a delta H of positive 226.7 kilojoules. So my answer is this. Again, this is a hard reaction to measure the delta H of, but all these other three kind of simple steps are easy to measure. So if I take these values, which we know pretty well, and just change them, whether it's multiplying them by 2, reversing their sign, leaving them the same, and then adding up my new delta H's, I can get the delta H for this reaction. Okay, and that is Hess's law. The next thing we're going to look at is basically heats of formation. So this is going to be I. Probably won't be able to get dots in there. Sometimes this is difficult and other times it's not. But anyways, so II, standard heats of formation. Standard heat of formation. So standard heats of formation are typically listed like this. Delta H, and then there's a little subscript F with a little 0 at the top. So the H refers to enthalpy, the F refers to formation, and then the little knot sign, is the way you pronounce this, is the standard sign. Okay? So again, H is enthalpy, HF, this F is formation, and the little knot sign at the top is standard. Standard for these conditions would be 25 degrees Celsius. If we're talking about solutions, or if we're talking about just amounts, it would be less temperature, be 1 atmosphere of pressure. If we're talking about a solution, the molarity, so if we think back in terms of brackets, would be 1 molar. And those would be standard conditions. Okay? And really this sets up like this. Delta H of reaction equals the sum, which here's our sigma sign, I think we referred to it a couple weeks ago, but it's basically the sum of the delta H knots of products. We're going to add all those up, because it's the sum of, minus the sum of delta F naught of the reactants. Okay, and that is our equation. Okay, in your book, if you go to table 6.4, this is just a list of standard enthalpies. If you look at this, notice there's lots of them that are zeros. Elements or compounds in their most stable state have standard enthalpies of formation of 0, because that's the way they are most stable, so that it takes no heat to make them that way. That's just the way they generally are. But table 6.4 is just in your book. You'll really be referring to appendix 3 for a lot of the homework problems this unit. Okay? But the way one of these is going to work, we're just going to do a quick example. Example is going to be methane plus, and then state symbols are super important in this unit because depending on what the state symbol is, stuff could change quite a bit. So methane as a gas plus oxygen as a gas is just going to be combustion, so we're going to get carbon dioxide and water. And it's always carbon dioxide gas and typically water vapor, which is going to be a liquid. And if we balance this equation, we end up having 2 waters and 2 oxygens, and the others are 1s. Okay? So if we look at this and kind of begin looking at delta H's of formation, and these are just, we're going to be looking at these in a book. our products, obviously, are on the right, and reactants are on the left. So I'm going to look up in the book, what is carbon dioxide's standard heat of formation? And I'm going to find that it is negative 393.5 kilojoules per mole. And notice I have 1 mole of this. Okay? So I'm just going to put that in brackets, or parentheses. I'm going to have brackets way out here. We're really multiplying this by 1 because we have a coefficient of 1. Okay? And I'm going to add that to water. Alright? And water as a liquid has a heat of formation of negative 285.8 kilojoules per mole. Alright, but notice we have 2 moles of this, so we're going to multiply that by 2. So this is my sum of formation of products, and I'm going to subtract my reactants from my products. So methane, again, I have 1 of those. So if I look at methane in the back of the book, I'm going to find that it's negative 74.9 kilojoules per mole. And then I have 2 oxygens. And because oxygen typically comes as oxygen gas, if we look at this up in the back of the book, we're going to find that oxygen is 0 kilojoules per mole. So simple algebra at this point, 1 times negative 393.5 plus 2 times negative 285.8. And then we're going to subtract a negative, so we end up adding 74.9. But our end result is that this equals negative 890 kilojoules. And we might put per mole. Generally, answers in the back are going to be per mole, because again, this number is our delta H that we might see at the end of our equation. Usually this might pop up right here. Alright, so if we were reacting as far as stoichiometry goes, 2 moles of water, it gives off negative 890 kilojoules. It's exothermic. But this is also 1 mole of carbon dioxide. Okay, so this value is stoichiometrically dependent, okay, based on our balanced chemical equation. I think that's all I want you to know on H of F. Again, it's 0. There is no value for elements in their most stable standard state. Okay? And I think that is it for podcast 8.3. First 2 ways to measure it are tonight. We'll see a 3rd way tomorrow night, and that is it. So enjoy your evenings, and I will see you tomorrow.